So here's something that might surprise you. Thermodynamics. This word that sounds so intimidating, so textbook heavy, so much like something you'd rather not think about. It's actually about the most ordinary thing in the world. It's about heat. It's about why your coffee gets cold, why your car moves, why you need to eat breakfast, why the stars shine. It's about the single most universal experience any human being has ever had, which is that things change, energy moves, and nothing stays the same forever. And the story of how we figured all of that out, how we turned those everyday observations into a set of laws so fundamental that nothing in the universe seems to violate them. That story is one of the wildest, most human, most dramatic tales in all of science. But let's not get ahead of ourselves. Let's start somewhere simple. Let's start with you, right now. Lying there, maybe under a blanket, maybe feeling the warmth of your own body settling into the mattress. That warmth? That's thermodynamics. Your body is a heat engine. You ate food today, your cells broke down the chemical bonds in that food, released energy, and some of that energy became useful work. Your muscles moved, your brain fired, your heart pumped, and some of it, a lot of it actually, became heat. Waste heat. And that heat is radiating off your skin right now, warming the air around you, warming the sheets, slowly dissipating into the room. You are, in a very real sense, a thermodynamic system. And the fact that you can't get that heat back, the fact that it flows outward and disperses and becomes less and less useful, that's one of the deepest truths in all of physics. But we'll get there. We'll get there slowly. For now, let's go back. Way back. Because humans have been thinking about heat for as long as there have been humans. Fire was the first technology, really. Before the wheel, before agriculture, before language maybe, there was fire. And fire is pure thermodynamics, a chemical reaction releasing energy as heat and light. But for most of human history, nobody had any idea what heat actually was. They knew fire was hot. They knew the sun was warm. They knew that if you rubbed your hands together fast enough, they'd get warmer. But what was heat? What was this invisible thing that flowed from hot objects to cold ones? The ancient Greeks had some ideas, as they always did. Heraclitus, around 500 BC, thought fire was the fundamental element, that everything was in a state of flux, constantly transforming. There's something almost poetic about that, and honestly, he wasn't entirely wrong. Not about fire being an element, but about the transformation part. Aristotle later categorized heat as a quality, not a substance. Hot and cold were properties that objects could have, like color or weight, and that view stuck around for a remarkably long time. For nearly 2,000 years, people didn't really push much further than Aristotle on this question. But then something changed. And this is where the story starts to get really interesting. In the 1600s and 1700s, people started doing something radical. They started measuring heat, not just feeling it, not just philosophizing about it, but actually quantifying it. And that required a tool that didn't exist for most of human history, the thermometer. Now, who invented the thermometer? That's actually a surprisingly messy question. Galileo, around 1593, built something called a thermoscope, basically an open glass tube with a bulb at the top, inverted into a dish of water. As the air in the bulb warmed or cooled, it expanded or contracted, pushing the water level up or down. It worked, sort of, but it was also affected by air pressure, so it wasn't really measuring temperature alone. It was measuring some confusing combination of temperature and atmospheric pressure, and nobody fully understood the difference yet. Still, it was a start. It was the first time someone said, "I want to put a number on how hot something is." Over the next century, other inventors refined the idea. Santorio, an Italian physician and a contemporary of Galileo, may have been the first to put a scale on a thermoscope. Then, in 1654, Ferdinando II de' Medici, yes, from that Medici family, sponsored the development of sealed liquid and glass thermometers in Florence. These were filled with alcohol, and because they were sealed, they weren't affected by air pressure. That was a big deal. Suddenly, you had a device that was actually measuring temperature reliably. But here's a problem nobody had solved yet. What numbers do you put on the scale? Think about that. You have a tube of liquid that goes up when it's hot and down when it's cold. Great. But where's 0? Where's 100? What do those numbers even mean? This is one of those problems that seems trivial once it's solved, but was genuinely confusing at the time. Daniel Gabriel Fahrenheit, a Polish-born Dutch instrument maker, tackled this around 1714. He was a meticulous craftsman, obsessive about precision, and he switched from alcohol to mercury, which expanded more uniformly and could measure higher temperatures. For his scale, he chose 3 reference points. The coldest temperature he could reliably produce in his lab, a mixture of ice, water, and ammonium chloride, which he set at 0. The freezing point of plain water, which he set at 32, and human body temperature, which he set at 96. The numbers seem arbitrary, and honestly, they kind of are. There are various theories about why he chose those specific values. Some historians think he was trying to avoid negative numbers in everyday weather measurements. Others think he was working with a scale that divided nicely by certain fractions. The exact reasoning is debated. But the important thing is that he gave the world a standardized, reproducible temperature scale. And mercury thermometers built by Fahrenheit were so precise, so beautifully crafted, that they became the gold standard across Europe. Then in 1742, Anders Celsius, a Swedish astronomer, proposed a different scale. And here's a fun detail. His original scale was actually inverted from what we use today. He set the boiling point of water at 0 and the freezing point at 100. It was flipped. Other scientists, including Carl Linnaeus, yes, the guy who classified all living things, later reversed it to the version we know, where 0 is freezing and 100 is boiling. Makes more sense that way, right? Bigger number, more heat. Simple. But here's the thing. Having a thermometer, having a way to measure temperature, that was just the beginning. Because temperature and heat are not the same thing, and figuring out the difference between them was one of the great intellectual struggles of the 1700s. Think about it this way. You can heat a cup of water and a bathtub of water with the same flame. The cup gets hot fast. The bathtub takes forever. But if they both reach the same temperature, they're at the same temperature. Yet the bathtub clearly contains more heat, more thermal energy. So temperature is telling you something about the intensity of heat, the concentration of it, but not the total amount. That distinction between temperature and what we'd now call thermal energy or heat content took a surprisingly long time to untangle. The person who really cracked this open was a Scottish chemist named Joseph Black, working in Glasgow in the 1750s and 1760s. Black was a careful, quiet, methodical scientist, not flashy, not dramatic, but deeply rigorous. And he noticed something that everyone had seen, but nobody had really explained. When you heat ice, it warms up. Fine. But then, when it reaches the melting point, something strange happens. You keep adding heat, and the temperature stops rising. The ice just sits there, melting, absorbing heat, but not getting any hotter. The thermometer doesn't budge. All that energy is going somewhere, but it's not showing up as a temperature increase. Where is it going? Black called this latent heat, from the Latin word for hidden heat, energy that was being absorbed by the ice to change its state from solid to liquid without changing its temperature. And the same thing happens when water boils. You heat water to 100 degrees Celsius, and then it just stays there, bubbling away, absorbing enormous amounts of energy as it transforms from liquid to gas. But the temperature holds steady at 100. This was a genuinely profound insight. It meant that heat wasn't just about temperature. It meant that energy could be absorbed by a substance and used to rearrange its internal structure, to break the bonds holding molecules in a rigid lattice, or to free them from the liquid state entirely, without making the substance any hotter. Think about what that means for a second. You're pouring energy into something, and the thermometer says nothing is happening. But something is happening. Something fundamental is changing inside the material. You just can't see it on the temperature scale. Black also developed the concept of specific heat, the idea that different materials require different amounts of heat to raise their temperature by the same amount. A kilogram of water takes a lot more energy to warm up by 1 degree than a kilogram of iron does. Water has a high specific heat. Iron has a low one. This is why the ocean moderates coastal climates. Water absorbs and releases enormous amounts of heat without changing temperature very much. And it's why a metal pan handle gets scorching hot in seconds while the wooden handle stays cool. Different materials, different relationships with heat. Now, all of this, thermometers, latent heat, specific heat, this was the groundwork, the careful, painstaking measurement phase. Scientists were learning to quantify heat, to track it, to see where it went, and how much of it was needed for different tasks. But the really big question, the one that would launch thermodynamics as a true science, was still lurking in the background. And it wasn't a question that came from a laboratory. It came from a factory. Because right around the time Joseph Black was puzzling over latent heat in Glasgow, something extraordinary was happening just down the road, almost literally. James Watt, a young instrument maker at the University of Glasgow, was asked to repair a model of a Newcomen steam engine. And this is one of those moments in history where the right person encounters the right problem at exactly the right time. The Newcomen engine had been around since about 1712. Thomas Newcomen, an English ironmonger, basically a hardware dealer, had built it to pump water out of mines, and it worked. It was a real, functioning steam engine, decades before Watt. But it was spectacularly inefficient. It guzzled coal. The way it worked was simple but wasteful. Steam was injected into a cylinder, pushing a piston up, and then cold water was sprayed directly into the cylinder to condense the steam, creating a partial vacuum that let atmospheric pressure push the piston back down. Up, down, pumping water out of mines one stroke at a time. The problem, and this is what Watt noticed, was that you were heating the cylinder with steam and then immediately cooling it with cold water, over and over and over. Every single cycle, you had to reheat the cylinder walls from cold back up to the temperature of steam. All that energy, all that coal, was being wasted just reheating the metal of the cylinder itself. It wasn't doing useful work. It was just fighting the thermal mass of the iron. Watt understood this, because he understood Joseph Black's ideas about specific heat and latent heat. He knew exactly how much energy was being wasted. And in 1765, while taking a walk on Glasgow Green on a Sunday afternoon, at least that's how the story goes, the solution hit him. What if you didn't condense the steam inside the working cylinder at all? What if you had a separate condenser, a second chamber, connected to the main cylinder by a valve? You'd keep the main cylinder hot all the time, and the condenser cold all the time, and just shuttle the steam between them. That way you'd never waste energy reheating the cylinder. It was elegant, it was brilliant, and it was directly inspired by the science of heat that Black had been developing. Watt and Black actually knew each other. Black had even lent Watt money to pursue his experiments. This was science and engineering feeding each other right there in 18th century Glasgow. But here's what's fascinating. Watt built a better engine. He made it dramatically more efficient. He changed the world. The Industrial Revolution runs on Watt's engine, essentially. Factories, mills, railways, steamships, all of it flows from this moment. And yet, neither Watt nor anyone else at the time had a real theory of what was happening. They knew heat made engines work. They knew efficiency mattered, but they didn't have a framework, a set of laws, that explained why. They didn't have thermodynamics yet. That was still coming. And it would come from the most unexpected place. Not from Britain, the land of steam and industry, but from France. From a young military engineer with a famous father, a man who would write one of the most important books in the history of science and then die almost completely unknown at the age of 36. His name was Sadi Carnot, and his story is one of the most bittersweet in all of science. Sadi Carnot was born in 1796, right in the thick of revolutionary France. His father was Lazare Carnot, sometimes called the Organizer of Victory, a brilliant mathematician and military strategist who had essentially saved the French Republic by reorganizing its armies during the Revolutionary Wars. Lazare was also a serious scientist in his own right, someone who had written important work on the efficiency of machines, particularly water wheels, and how to get the most useful work out of a mechanical system. So young Sadi grew up in a household where military strategy and engineering science were dinner table conversation. Imagine that childhood. Your father is one of the most powerful men in France, a man who thinks about war and machines with equal rigor, and you're absorbing all of it. Sadi entered the prestigious École Polytechnique in Paris at 16, which was the elite training ground for French engineers and scientists. He studied under some of the best minds in the country. But here's the thing about Carnot's life. It was shaped by politics in ways that kept pulling him away from science. After Napoleon's final defeat at Waterloo in 1815, the Carnot family fell out of favor. Lazare was exiled. Sadi, despite being a trained military engineer, found himself on half pay with not much to do. He was essentially sidelined, a young officer in a peacetime army that didn't particularly want him around because of his family name. And this is where something remarkable happens. Instead of wallowing in frustration, Carnot turned his attention to a question that had been nagging at him. He'd been watching what was happening across the English Channel. Britain was surging ahead industrially, and the engine driving that surge, literally, was the steam engine. France had steam engines too, but they were mostly imported or copied from British designs, and they weren't as good. Carnot wanted to understand, at the deepest possible level, what made a steam engine work. Not just how to build a better one, but what were the fundamental limits. Was there a ceiling on how efficient an engine could be? And if so, what determined that ceiling? Now, think about what a bold question that is. In the 1820s, nobody had even properly defined what energy was. The word energy, in its modern scientific sense, hadn't been coined yet. People were still arguing about whether heat was a substance, this invisible fluid called caloric that supposedly flowed from hot things to cold things, or whether it was some kind of motion. Carnot actually believed in caloric theory, which turned out to be wrong. And yet, and this is the wild part, he managed to arrive at profoundly correct conclusions despite starting from a flawed premise. That almost never happens in science, and it tells you something about the sheer power of his reasoning. In 1824, Carnot published a slim book called Reflections on the Motive Power of Fire. That title sounds almost poetic, doesn't it? The motive power of fire. What he meant was, what is it about heat that lets you get useful work out of it? And the way he approached the problem was genuinely revolutionary. He didn't focus on any particular engine, not Watt's engine, not any specific design. Instead, he imagined an idealized engine, a perfect engine, one that wasted nothing. We now call this the Carnot engine, and it's one of the most important thought experiments in physics. Here's how he thought about it. He drew an analogy to a water wheel, which makes sense given his father's work on exactly that subject. A water wheel produces work because water falls from a height. The water starts high, it ends low, and the wheel captures some of that falling motion as useful work. The amount of work you can extract depends on how far the water falls, the height difference. Carnot said heat engines work the same way, except instead of water falling through a height difference, you have heat falling through a temperature difference. Heat flows from something hot to something cold, and an engine sits in the middle and captures some of that flow as work. Let that sink in for a moment. It's such a clean, beautiful idea. You need a hot source and a cold sink, and the engine lives between them. No temperature difference, no work. It doesn't matter what the engine is made of, what fuel it burns, whether it uses steam or air or anything else. The fundamental thing that makes any heat engine work is a temperature difference. That's it. That's the deep truth Carnot uncovered. And then he went further. He asked, for a given temperature difference, what's the maximum amount of work you could possibly extract? And he showed that this maximum depends only on the temperatures of the hot source and the cold sink. Nothing else. Not the working fluid, not the mechanical design, not the cleverness of the engineer. Just the two temperatures. A perfect engine operating between a flame at 1,000 degrees and a cold reservoir at room temperature has a fixed maximum efficiency, and no engine, no matter how brilliantly designed, can ever exceed it. This is staggering when you really think about it. Carnot was 28 years old, working mostly alone, using a theory of heat that was fundamentally incorrect, and he discovered a universal law of nature. He discovered that there are absolute limits to what engines can do, limits imposed not by our engineering skill, but by the nature of reality itself. You can't engineer your way past the Carnot limit. You can get closer to it, sure. You can reduce friction, minimize heat losses, design better seals and valves, but you can never beat it. It's like a speed limit written into the fabric of the universe. And here's what makes the story heartbreaking. Almost nobody noticed. The book sold maybe a couple hundred copies. A few engineers read it and found it interesting but didn't fully grasp its significance. The scientific establishment largely ignored it. Carnot continued his quiet life in Paris, thinking, scribbling in notebooks, refining his ideas. In those private notebooks, which weren't discovered until much later, there's evidence that he was actually moving away from caloric theory and toward the idea that heat is a form of motion, which is correct. He was also groping toward something like the conservation of energy, years before anyone else. We'll never know how far he would have gone, because in 1832, at the age of 36, Sadi Carnot died during a cholera epidemic in Paris. As was customary during cholera outbreaks, most of his personal belongings were burned, including many of his papers. Just gone. One of the greatest scientific minds of the 19th century, and we lost not only the man, but most of his unpublished work. It would take more than 20 years for someone to fully appreciate what Carnot had done, and that someone was a quiet, meticulous German physicist named Rudolf Clausius. But before we get to Clausius, there's another thread we need to pick up, because while Carnot was thinking about ideal engines in France, something equally important was brewing in the world of experimental science: the question of what heat actually is and whether it could be converted into other forms of, well, something. That something didn't have a name yet, but it was about to get one. You see, by the 1840s, there were several people, working in different countries and different contexts, all circling around the same enormous idea. And the idea was this: that there's a single quantity in nature, something we now call energy, that can take many different forms, and that it's never created or destroyed, only transformed from one form to another. Heat can become motion. Motion can become heat. Chemical reactions release heat. Electricity can produce motion. Light carries something. And all of these are different faces of the same underlying thing. The person who deserves perhaps the most credit for nailing this down experimentally was James Prescott Joule, a brewer's son from Manchester, England. And I love Joule's story because he wasn't a university professor. He wasn't part of the scientific establishment. He was a wealthy young man who ran his family's brewery and did physics experiments essentially as a hobby. Though calling it a hobby undersells the extraordinary precision and dedication he brought to it. Joule became obsessed with one question: could you measure the exact relationship between mechanical work and heat? If you stir water with a paddle, the water gets slightly warmer. Everyone knew that. Friction produces heat. Rub your hands together and you feel it. But could you put a precise number on it? Could you say that this exact amount of mechanical work always produces that exact amount of heat? Starting in the early 1840s, Joule built increasingly refined versions of an apparatus that's become iconic in physics. Picture a tall, insulated container of water. Inside the water, there are paddle wheels, little vanes that can spin. Connected to these paddles by a system of strings and pulleys are weights. When you let the weights fall, they turn the paddles, which churn the water. The churning, the friction of the paddles against the water, heats the water up, and Joule measured that temperature rise with extraordinary care, using thermometers sensitive to tiny fractions of a degree. The temperature changes were minuscule. We're talking about increases of maybe a fraction of a degree Fahrenheit. To detect them reliably, you needed incredibly precise thermometers and incredibly careful experimental technique, and Joule had both. He ran these experiments over and over, varying the weights, varying the amount of water, checking and rechecking, and what he found was that the relationship was exact. A specific amount of mechanical work, weights falling through a specific distance, always produced the same amount of heat in the water. Always. It didn't matter how fast or slow the paddles turned, didn't matter what day of the week it was. The conversion ratio was fixed. This number, the mechanical equivalent of heat, was Joule's great contribution. He established that heat and mechanical work are interconvertible, and he measured the exchange rate. It's like discovering that dollars and euros have a fixed conversion rate that never changes, except this is a conversion rate built into the laws of physics. But here's the thing. When Joule first presented his results to the British Association for the Advancement of Science in 1843, the reception was lukewarm. Polite silence mostly. People weren't sure what to make of this brewer who claimed to have measured something so fundamental. It took years of persistent experimentation and increasingly precise results before the scientific world started paying attention. And one of the key moments came in 1847 when Joule gave a talk in Oxford and a young Irish-Scottish physicist named William Thomson happened to be in the audience. Thomson was skeptical at first. He was a Carnot enthusiast and wasn't sure Joule's ideas about heat being convertible were compatible with Carnot's framework. But he was intrigued enough to keep thinking about it. And that tension, that apparent contradiction between what Carnot had said and what Joule was showing, would turn out to be one of the most productive contradictions in the history of science. Because think about what was at stake. On one hand, you had Carnot's beautiful framework, which said that heat flows from hot to cold, and that's what drives engines. Heat is like a fluid that falls from a high temperature to a low temperature, and you extract work from that fall, the way a water wheel extracts work from falling water. And crucially, in Carnot's picture, the heat itself is conserved. It doesn't get used up. It just moves from hot to cold. On the other hand, you had Joule standing there with his paddle wheel apparatus and his meticulous measurements, saying no, heat and work are interconvertible. You can destroy work and create heat. You can, at least in principle, destroy heat and create work. Heat is not conserved. It can be created and consumed. So who was right? Because they couldn't both be right. If heat is conserved, as Carnot assumed, then Joule's experiments don't make sense. And if heat can be converted into work and vice versa, as Joule showed, then Carnot's whole framework seems to be built on a false premise. And yet, Carnot's conclusions, his predictions about the maximum efficiency of engines, the importance of temperature difference, those all matched reality. They worked. Engineers were building better engines based on Carnot's insights, and the results held up. So you had a theory built on a wrong assumption that somehow gave right answers, and you had experimental results that contradicted the assumption but didn't yet have a theory to house them. That's the kind of mess that keeps physicists up at night. And the two people who sorted it out, working independently and from very different starting points, were William Thomson and Rudolf Clausius. Let's stay with Thomson for a moment, because his journey through this contradiction is really instructive. Thomson, who would later become Lord Kelvin, and yes, that's the Kelvin of the Kelvin temperature scale, was born in Belfast in 1824, the same year Carnot published his book, which is a nice coincidence. His family moved to Glasgow when he was young, and his father was a mathematics professor at the University of Glasgow. So Thomson grew up steeped in rigorous mathematical thinking. He was a prodigy, frankly. He matriculated at the university at age 10. He published his first scientific paper at 16. By his early 20s, he was already a professor of natural philosophy at Glasgow, and he would hold that position for over 50 years. Thomson was deeply committed to Carnot's framework. He'd gotten hold of Carnot's book, which was still obscure at that point, through a French physicist named Clapeyron, who had reformulated Carnot's ideas in more mathematical language. And Thomson saw the power in it. He saw that Carnot's reasoning led to something profound, the idea that there must be an absolute zero of temperature, a point below which you cannot go, because if you could, you'd be able to build an engine that violated Carnot's principles. Thomson worked this out in the late 1840s, and in 1848, he proposed what we now call the absolute temperature scale, the Kelvin scale, which starts at absolute zero, roughly minus 273 degrees Celsius. That was a direct consequence of taking Carnot seriously. But then there was Joule, with his paddle wheels and his falling weights, showing that heat and work are the same kind of thing. And Thomson couldn't ignore Joule's results. The data was too good. So Thomson sat with this contradiction for years. He wrote about it, agonized over it, acknowledged publicly that he didn't know how to resolve it. And I think that's worth pausing on, because it's rare and admirable for a scientist to say, publicly, I see two things that seem to contradict each other, and I don't know the answer. Most people pick a side and dig in. Thomson held both ideas in his mind and waited. The resolution, when it came, arrived first from across the English Channel. Rudolf Clausius was a German physicist born in 1822 in Köslin, Prussia, what's now Koszalin, Poland. He'd studied at the University of Berlin and was working as a professor in the German-speaking academic world, which at that time was arguably the most rigorous scientific environment on the planet. Clausius read Carnot's work. He knew about Joule's experiments, and in 1850, he published a paper that cut through the whole mess with remarkable clarity. The paper's title was On the Motive Power of Heat, a deliberate echo of Carnot's title. And what Clausius did was elegant. He said, essentially, Carnot was right about some things and wrong about others. Joule is right that heat can be converted into work. Heat is not conserved. But Carnot's key insight, that heat naturally flows from hot to cold, and that you can extract work from this flow, and that there's a maximum efficiency. All of that survives. You just have to restate the foundation. Here's how Clausius did it. He accepted Joule's principle, that heat and work are interconvertible, that there's a fixed exchange rate, that energy in total is conserved. This is what we now call the first law of thermodynamics. Energy cannot be created or destroyed, only converted from one form to another. When you burn coal under a boiler, you're converting chemical energy into heat. When that heat drives a piston, you're converting some of that heat into mechanical work. The total amount of energy, heat plus work plus every other form, stays the same. Always. This is the great conservation law, and Joule's paddle wheel experiments were among the key pieces of evidence for it. But then Clausius added something else, something that Joule's work alone couldn't explain. He said, even though you can convert heat into work, you can't do it with perfect efficiency. There's always some heat that flows from the hot source to the cold sink without doing any work at all. And this isn't because of friction or bad engineering. It's a fundamental law of nature. Heat flows spontaneously from hot to cold, never the other way around. You can force heat to flow from cold to hot. That's what a refrigerator does, but it costs you work to do it. Left to its own devices, heat always goes downhill, from high temperature to low. This is, in its earliest form, the second law of thermodynamics. And I want you to sit with that for a moment, because the second law is one of those things that sounds almost too obvious to be profound. Of course, hot things cool down. Of course, Heat flows from hot to cold. You don't need a German physicist to tell you that your coffee gets cold if you leave it on the counter. But the profundity isn't in the observation. It's in the consequences. Because what the second law really says is that there's a directionality to nature. Things happen in one direction and not the other. Your coffee cools down, but it never spontaneously heats back up by absorbing heat from the cooler room. An egg falls off the counter and breaks, but broken eggs never reassemble themselves and jump back up. The first law, conservation of energy, wouldn't forbid any of those reverse processes. The energy books would balance perfectly fine if your coffee spontaneously got hotter and the room got cooler by the same amount. Conservation of energy says nothing about direction. It's the second law that gives time its arrow. Now, Clausius stated this initially in a fairly specific way. Heat cannot spontaneously pass from a colder body to a warmer one. That's it. Simple sentence. But over the next 15 years, he would develop this idea into something much more powerful and much more abstract. He would invent a new quantity, a new way of measuring something about the state of a system, and he would give it a name that he deliberately chose from the Greek word for transformation. He called it entropy. And entropy is honestly one of the most misunderstood concepts in all of science. People throw the word around. Entropy means disorder. Entropy means chaos. Entropy means everything falls apart. And those aren't exactly wrong, but they're not exactly right either. So let's take this slowly. What Clausius actually defined was this. When a small amount of heat flows into a system at a certain temperature, the entropy of that system increases by an amount equal to the heat divided by the temperature. That's the mathematical definition. Heat in divided by temperature equals change in entropy. And what Clausius showed, and this was his masterwork, developed over papers published from the 1850s through 1865, was that in any real process, the total entropy of the universe either stays the same or increases. It never decreases. This is the second law restated in its most general form. The entropy of the universe tends toward a maximum. Think about what that means in practical terms. Every time something happens, every time an engine runs, every time you stir cream into coffee, every time a star burns, every time you breathe, the total entropy of everything involved either stays the same or goes up. And stays the same only happens in idealized, perfectly reversible processes that don't actually exist in the real world. In reality, entropy always increases. Always. This is why perpetual motion machines are impossible. Not just difficult, not just beyond our current engineering. Impossible, forbidden by the second law. Any real machine, no matter how well designed, generates some entropy, wastes some energy as heat that can't be recovered, and gradually runs down. And here's where it connects back to Carnot, beautifully. Remember Carnot's result, that there's a maximum efficiency for any heat engine, and it depends only on the temperatures of the hot source and the cold sink. Clausius showed that this maximum efficiency corresponds exactly to a process where entropy stays constant, a reversible process. Any real engine, with friction and turbulence and imperfect insulation, generates extra entropy, and that extra entropy is directly connected to the wasted heat, the inefficiency. Carnot's limit is the entropy limit. The reason you can never build a perfectly efficient engine is that you'd have to run it without increasing entropy, and that's impossible in the real world. So Clausius took Carnot's insight, stripped away the wrong assumption about heat being conserved, replaced it with Joule's correct principle of energy conservation, and then added this new, deeper principle about entropy, always increasing. And the result was a framework, the first and second laws of thermodynamics, that was more powerful than either Carnot's or Joule's ideas alone. The first law tells you that energy is conserved. The second law tells you which direction things go. Together, they explain why engines work, why they have limits, why heat flows the way it does, and why the universe has a direction. Clausius himself summarized the two laws with beautiful conciseness in 1865. He wrote, "The energy of the universe is constant. The entropy of the universe tends toward a maximum." 2 sentences. That's it. The entire foundation of thermodynamics in 2 sentences. And there's something almost poetic about them. One law about what stays the same. One law about what always changes. Now, Thomson arrived at very similar conclusions around the same time, working independently. His version of the second law was stated a bit differently. He said it's impossible to build a device that does nothing but convert heat into work. In other words, you can't just take heat from a single source and turn all of it into useful work without some of it being dumped somewhere colder. This sounds different from Clausius's statement about heat not flowing from cold to hot, but they're actually equivalent. You can prove that if one is true, the other must be, and vice versa. They're 2 sides of the same coin, 2 different windows into the same deep truth about nature. And Thomson took this in a direction that was frankly a little unsettling. He started thinking about the long-term consequences of the second law. If entropy always increases, if useful energy is always being degraded into waste heat, then the universe as a whole is running down. Every star that burns is converting concentrated energy into diffuse heat. Every engine, every process, every living thing is contributing to this one-way slide toward a state of maximum entropy, where everything is the same temperature and nothing interesting can happen anymore. Thomson called this the heat death of the universe, and when he wrote about it in the 1850s, it genuinely disturbed people. The idea that the universe had an expiration date, that all the energy and activity and life would eventually peter out into a lukewarm, featureless nothing. That was a philosophical bombshell. But let's not get too existential here. Let's come back to something more concrete, because while Clausius and Thomson were working out the theoretical foundations, something practical was happening that would test these ideas in the most demanding way possible. The steam engine was evolving. And the question that engineers were now asking, armed with this new understanding of thermodynamics, was, how close can we actually get to Carnot's limit? How efficient can a real engine be? And to answer that question, we need to talk about a Scottish engineer named William Rankine, who was doing something that might sound unglamorous, but was absolutely essential. He was building the mathematical tools that let you actually calculate what happens inside a real engine when real steam flows through real pipes and expands against real pistons. Rankine was a fascinating character. Born in Edinburgh in 1820, he was one of those people who seemed to straddle 2 worlds, the world of pure theory and the world of getting your hands dirty. He'd trained as a civil engineer, worked on railways and harbors, but he had this deep mathematical ability that set him apart from most practicing engineers of his time. And in the 1850s, while Clausius was refining entropy and Thomson was worrying about the heat death of the universe, Rankine was sitting down and working out, in painstaking detail, how you could take all of this beautiful theory and turn it into something an engineer could actually use to design a better engine. Here's the thing about thermodynamics up to this point. Carnot had given you the ceiling, the absolute maximum efficiency any engine could achieve between two temperatures. That was profound, but it was also abstract. It told you where the finish line was, but it didn't tell you how to run the race. If you were an engineer in 1855 and someone handed you Carnot's theorem, you'd say, "Great. So my engine can never be more than, say, 40% efficient. But my engine is currently running at maybe 8%. How do I get from 8 to something closer to 40? What specific changes do I make? What happens to the steam at each stage of the process?" That's the gap Rankine filled. What Rankine did was develop what we now call the Rankine cycle, which is a model of how a real steam power plant actually works, broken down into distinct steps that you can analyze thermodynamically. And the beauty of it is that it's still used today. If you're an engineering student right now studying power generation, you're learning the Rankine cycle. It's that fundamental. So let me walk you through it, because it's actually quite elegant once you see the logic. Imagine a simple steam power plant. You've got four main components: a boiler, a turbine, or in the old days, a piston engine, a condenser, and a pump. And the working fluid, the water, goes around and around through these four components in a loop. It's a closed cycle. Start with the boiler. You take liquid water and you heat it up using coal or gas or nuclear fission or concentrated sunlight, whatever your heat source is. The water boils, turns to steam, and that steam is at high temperature and high pressure. Remember Joseph Black and latent heat? This is exactly where that matters. You're pumping in all that energy to change the water from liquid to gas, and that energy is now stored in the steam, ready to do work. Next, that high-pressure steam flows into the turbine. As it expands through the turbine, it pushes against the blades, or in the old days, against the piston, and that's where you extract work. The steam gives up energy. Its pressure drops. Its temperature drops. It comes out the other side of the turbine as low pressure, cooler steam, maybe mixed with some liquid droplets. Then, that spent steam goes into the condenser. This is where you reject heat to the environment, to a river, to the atmosphere through cooling towers, whatever. The steam condenses back into liquid water. And here's where Carnot's insight is staring you right in the face. You have to reject some heat. You can't convert all of it to work. The condenser is where the second law of thermodynamics shows up in your engineering drawings. It's the unavoidable tax. Finally, the liquid water gets pumped back up to high pressure by a feed pump, and it goes back into the boiler to start the whole cycle again. Pump, boil, expand, condense, round and round. Now, what Rankine did was figure out how to calculate the energy at each of these stages. How much heat goes in at the boiler, how much work you get out of the turbine, how much heat you reject at the condenser, how much work the pump requires. And from those numbers, you can calculate the efficiency of the whole cycle, the fraction of heat input that actually becomes useful work. And when you do that calculation, you get a number that's always less than Carnot's ideal, because the Rankine cycle involves real processes that generate entropy. The steam doesn't expand perfectly. There's friction. There's heat loss through pipe walls. But the Rankine cycle gives you a realistic target, and more importantly, it tells you where the losses are and what you can do about them. And this is where it gets really practical, really useful. Because once you have this framework, you can start asking smart questions. What if I raise the boiler temperature? The Rankine cycle math tells you exactly how much that improves efficiency. What if I lower the condenser temperature? Same thing. You can calculate the gain. What if I let the steam expand to a lower pressure before condensing it? You can model that too. Engineers suddenly had a quantitative tool for making design decisions, and it transformed the profession. One of the most important improvements that came out of this kind of thinking was superheating. See, in a basic Rankine cycle, the steam leaves the boiler right at the boiling point. It's what we call saturated steam. But as it expands through the turbine and cools down, some of it starts condensing back into liquid droplets. And those droplets are a problem. They erode the turbine blades, they reduce efficiency, they cause all sorts of mechanical headaches. So engineers realized, what if we keep heating the steam beyond the boiling point? Take it to, say, 500 degrees Celsius instead of the 200 or so where it boils at typical pressures. Now you've got what's called superheated steam, and when it expands through the turbine, it stays in the gas phase much longer before any condensation starts. You get more work out of each kilogram of steam, your turbine lasts longer, and your efficiency goes up. The thermodynamics predicted this, and the engineering confirmed it. Another trick that came from this analysis is reheating. You expand the steam partway through a high-pressure turbine, then send it back to the boiler to heat it up again, then expand it through a second, low-pressure turbine. It sounds like extra complication, and it is, but the efficiency gain is real and significant. Modern power plants use multiple stages of reheat, and every one of those design decisions traces back to the kind of systematic thermodynamic analysis that Rankine pioneered. But here's what I find really interesting about this period, the 1850s and 1860s. You've got this incredible convergence happening. The theorists, Clausius, Thomson, are working out the fundamental laws. The practical engineers, Rankine and others, are translating those laws into design tools. And meanwhile, the technology itself is evolving at a furious pace. Steam engines are getting bigger, more powerful, more efficient. Steam is being used not just for pumping water and driving factory machinery, but for locomotives, for ships, for generating electricity. The demand for better engines is intense, and for the first time in history, there's a real scientific framework to guide the improvements. It's not just trial and error anymore. You can actually predict, before you build anything, how a design change will affect performance. And this brings us to something that's easy to overlook, but is actually one of the most important practical consequences of thermodynamics, the concept of the thermodynamic property. Things like temperature, pressure, volume, internal energy, enthalpy, entropy. These are properties of the working fluid at any given moment, and they don't depend on how the fluid got to that state. That's a subtle but incredibly powerful idea. It means you can describe the state of steam using just a few numbers, and you can look up those numbers in tables, steam tables they're called, and use them to calculate everything you need to know about your engine's performance. The first really comprehensive steam tables were developed in the second half of the 19th century, and they were essentially the engineer's Bible. You want to know the enthalpy of steam at 300 degrees and 20 atmospheres of pressure? Look it up. You want to know how much energy you get when steam expands from one state to another? The tables tell you. This might sound mundane, but think about what it represents. All of that deep theoretical work by Carnot, Joule, Clausius, Thomson, Rankine, it got distilled into practical reference tables that a working engineer could use on a Tuesday afternoon to design a better boiler. That's the arc from pure science to applied engineering, and it happened remarkably fast. Maybe 50 years from Carnot's lonely pamphlet to engineers routinely using thermodynamic calculations in their daily work. Now, while all of this was playing out in the world of steam and heat engines, something else was brewing. A completely different approach to understanding the same phenomena. And this is one of my favorite parts of the whole thermodynamics story, because it involves one of the most brilliant and tragically underappreciated physicists who ever lived. I'm talking about Ludwig Boltzmann. And to understand what Boltzmann did, you have to first appreciate the question he was trying to answer. Thermodynamics, as Clausius and Thomson had formulated it, was a macroscopic theory. It dealt with bulk properties, the temperature of a gas, the pressure in a cylinder, the total entropy of a system. It didn't say anything about what was actually happening at the microscopic level. It didn't need to. The laws worked beautifully without any reference to atoms or molecules. But by the 1860s, the atomic theory of matter was gaining ground. The idea that gases were made up of enormous numbers of tiny particles bouncing around was being taken more and more seriously. James Clerk Maxwell, yes, the same Maxwell who unified electricity and magnetism, had worked out a statistical description of how fast the molecules in a gas move. Not every molecule moves at the same speed. Some are fast, some are slow, and Maxwell figured out the mathematical distribution, the bell curve-like shape that describes how many molecules are moving at each speed at any given temperature. Higher temperature means the whole distribution shifts toward faster speeds. It was a beautiful piece of work, and Boltzmann took Maxwell's ideas and ran with them in a direction that would fundamentally change what we mean by entropy, what we mean by the second law, and ultimately, what we mean by the arrow of time itself. Boltzmann was born in Vienna in 1844, and from an early age he was drawn to the deepest questions in physics. He was passionate, intense, sometimes combative in scientific debates, and he had this unshakable conviction that atoms were real, which, believe it or not, was controversial in the late 19th century. Some very prominent physicists and philosophers, people like Ernst Mach, argued that atoms were just a useful fiction, a mathematical convenience with no physical reality. Boltzmann thought that was absurd, and he spent his career trying to prove it by showing that the macroscopic laws of thermodynamics, the laws that everyone agreed were real, could be derived from the statistical behavior of enormous numbers of atoms. And the key insight, the one that changed everything, had to do with entropy. Clausius had defined entropy mathematically. Heat divided by temperature, integrated over a process. But what was entropy really? What did it mean physically? Clausius's definition was precise but abstract. It told you how to calculate entropy, but it didn't give you a picture, an intuition for what entropy actually is. Boltzmann provided that picture. And it's so elegant, so simple in its core idea, that once you hear it, you'll never forget it. Here's how to think about it. Imagine you have a box divided in half by a partition, and all the gas molecules are on the left side. You remove the partition. What happens? The gas expands to fill the whole box. You never, ever see the reverse. You never see all the molecules spontaneously rush back to the left side. But why not? The laws of physics that govern each individual molecule, Newton's laws of motion, work perfectly well in reverse. If you filmed a single molecule bouncing around and played the film backward, you couldn't tell the difference. Every individual collision is reversible. So why is the overall behavior so stubbornly one-directional? Boltzmann's answer was probability. Pure, overwhelming, crushing probability. Think about it this way. When all the molecules are on the left side of the box, that's one very specific arrangement. There's essentially one way to have every single molecule on the left. But there are astronomically many ways to have the molecules spread throughout the whole box. Some on the left, some on the right. in countless different configurations. The number of possible arrangements where the gas fills the whole box is so incomprehensibly larger than the number of arrangements where it's all on one side that the probability of spontaneously returning to one side is effectively zero. Not approximately zero, not really small. Effectively zero. We're talking about a number so tiny that if you wrote it as a fraction, the denominator would have more digits than there are atoms in the observable universe. You could wait 1 billion times the age of the cosmos, and you would never see it happen. Not once. The gas will stay spread out, filling the whole box, not because some mysterious force compels it, but because the odds of any other outcome are so absurdly, hilariously stacked against it that impossible is, for all practical purposes, the right word. And this is Boltzmann's great insight distilled into a single, beautiful equation. He wrote it as S equals K log W. That's it. 4 symbols. S is entropy. W, from the German word Wahrscheinlichkeit, which means probability, is the number of microscopic arrangements that correspond to a given macroscopic state. And K is a constant, now called Boltzmann's constant, a tiny number that bridges the scale between individual molecules and the bulk properties we can measure with thermometers and pressure gauges. The logarithm is there because it converts multiplication into addition, which makes entropy a quantity that adds up nicely when you combine systems. But the heart of it is that relationship between S and W. Entropy isn't some mysterious fluid. It isn't an abstract mathematical trick. Entropy is a count. It's a measure of how many different ways the microscopic pieces of a system can be rearranged while still looking the same from the outside. Let that settle for a moment. Think about your cup of coffee cooling on the nightstand. The heat energy in that coffee is carried by the jiggling of water molecules. When the coffee is hot and the room is cool, there's a very specific kind of arrangement. Fast-moving molecules concentrated in the cup, slower-moving molecules in the surrounding air. There are relatively few ways to achieve that particular split, but as heat flows from the coffee into the room, the energy spreads out, the temperature differences shrink, and the number of possible microscopic arrangements that are consistent with that more uniform temperature distribution absolutely explodes. The system isn't being pushed toward equilibrium by some force. It's falling into equilibrium the way a ball rolls downhill, toward the state that is overwhelmingly, crushingly more probable than any alternative. So the second law of thermodynamics, in Boltzmann's picture, isn't really a law in the way Newton's laws are laws. It's not a fundamental command built into the fabric of physics. It's a statistical truth. It's the observation that systems evolve toward more probable states because less probable states are so extraordinarily unlikely that they essentially never occur. And that's a subtle but profound shift. Clausius told you entropy always increases. Boltzmann told you why. And the why is just math. Combinatorics on a scale so vast it becomes certainty for all practical purposes. Now here's where this gets philosophically deep, and it's the kind of thing that kept Boltzmann up at night, probably much later than you're up right now. If the second law is statistical rather than absolute, then in principle, entropy could decrease spontaneously. A cup of coffee could get hotter while the room gets colder. All the air molecules in your bedroom could, for one terrifying instant, crowd into one corner and leave you in a vacuum. These things aren't forbidden by the fundamental laws of physics. They're just so improbable that they never happen in practice. But the fact that they're possible in principle, even if they never actually occur, was deeply unsettling to some of Boltzmann's contemporaries. And this is where his story gets painful. Boltzmann faced opposition that was, at times, vicious, and it came from serious, respected scientists. The most prominent was Ernst Mach, the physicist and philosopher whose name you might recognize from Mach numbers, the speed of sound and all that. Mach was a positivist. He believed that science should deal only with what can be directly observed and measured, and atoms in the 1870s and 80s could not be directly observed. Nobody had seen an atom. Nobody had photographed one. The atomic hypothesis was, to Mach, a useful fiction at best and unscientific speculation at worst. And here was Boltzmann, building his entire framework of statistical mechanics on the assumption that matter was made of discrete particles whose positions and velocities determined everything. Mach thought this was metaphysics, not physics. He wasn't alone. Wilhelm Ostwald, a prominent chemist, championed what he called energetics, the idea that energy, not atoms, was the fundamental reality, and that all of chemistry and physics could be described purely in terms of energy transformations without ever invoking invisible particles. The debates were fierce. There were public confrontations at scientific meetings. In 1895, at a gathering of the German natural scientists and physicians in Lübeck, Boltzmann found himself essentially defending the existence of atoms against a room that included many skeptics. It wasn't just intellectual disagreement. It became personal. Boltzmann felt isolated, attacked, misunderstood. He was a large, gregarious man with a sharp wit, but he was also prone to depression, and the sustained hostility took a real toll. And here's what makes this so tragic. Boltzmann was right. Atoms are real. His statistical interpretation of entropy was correct. His framework would become one of the pillars of modern physics. But he didn't live to see the vindication. In 1906, while on vacation with his family at Duino, near Trieste, Ludwig Boltzmann took his own life. He was 62 years old. The reasons were complex. He had long struggled with what was likely bipolar disorder, and his health was failing. But the decades of intellectual combat, the feeling that his life's work was being dismissed or ignored, surely weighed on him. Just a few years after his death, the tide turned decisively. Einstein's 1905 paper on Brownian motion provided strong evidence for the atomic hypothesis, and Jean Perrin's experiments in 1908 and 1909 confirmed it beyond reasonable doubt. By 1910, even Ostwald conceded that atoms were real. Boltzmann's equation, S equals K log W, is carved on his tombstone in Vienna. It sits there quietly, one of the most important equations in all of physics, a monument to a man who saw the truth before the world was ready to accept it. Let's sit with that for a moment, because it matters beyond the science. Boltzmann's story is a reminder that being right isn't always enough. The sociology of science, who gets heard, whose framework gets adopted, which ideas are considered legitimate, is as human and messy as any other human enterprise. And sometimes the people who see farthest suffer the most for it. But the ideas survived, and they grew. Boltzmann's statistical mechanics didn't just explain entropy. It opened an entirely new way of thinking about physical systems. Instead of tracking every individual particle, which is impossible for any real system, you could use probability distributions to describe the collective behavior of enormous numbers of particles. You could derive the properties of gases, liquids, and solids from first principles, starting with the behavior of individual molecules and building up. Temperature, in this picture, isn't a mysterious quality. It's a measure of the average kinetic energy of the molecules in a system. Pressure isn't a mysterious force. It's the collective effect of trillions of molecules bouncing off the walls of their container. Every macroscopic property you can measure with instruments emerges from the statistics of the microscopic world. And this connects to something you experience every day without thinking about it. When a weather forecaster tells you the temperature tomorrow will be 72 degrees, they're giving you a statistical summary of the average kinetic energy of the air molecules that will surround you. When you pump up a bicycle tire and it feels warm, that's because you've compressed the gas, forced the molecules closer together, increased the frequency of their collisions, and that shows up as a temperature rise. When you spray a can of compressed air and the can gets cold, the gas is expanding, the molecules are doing work pushing outward, they lose kinetic energy, and the temperature drops. These everyday experiences are statistical mechanics in action. Boltzmann gave us the language to understand them at the deepest level. Now, there's one more thread from Boltzmann's work that I want to pull on, because it leads somewhere genuinely strange and beautiful. Remember that the second law, in his statistical interpretation, tells us that systems evolve toward states of higher probability, toward higher entropy. This gives time a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. This is what physicists call the arrow of time, and it's one of the deepest puzzles in all of physics, because almost every other fundamental law is time-symmetric. Maxwell's equations, Newton's laws, even quantum mechanics, they all work the same whether time runs forward or backward. The second law is the great exception. It's the one law that distinguishes past from future. And Boltzmann himself grappled with this. If the microscopic laws are reversible, where does the arrow of time come from? His answer, essentially, was that it comes from initial conditions. The universe started, or at least the observable part of it started, in a state of extraordinarily low entropy. The Big Bang was an incredibly ordered, incredibly unlikely initial state. And everything since then has been the universe exploring the vastly larger space of higher entropy states, like the gas expanding to fill the box. We experience time flowing forward because we live in a universe that hasn't yet reached equilibrium, a universe still in the process of spreading out, cooling down, evening out. The arrow of time isn't written into the laws themselves. It's written into the boundary conditions, into the way things started. And that idea, honestly, is still being debated today. Physicists and philosophers argue about why the initial state was so special, whether it requires explanation, whether there might be regions of the universe where entropy runs the other direction and time effectively flows backward. These are open questions, live questions, the kind of thing people write papers about right now. But the framework for even asking them, the connection between entropy, probability, and the direction of time, that's Boltzmann's gift. So by the early 1900s, thermodynamics had this extraordinary double life. On one hand, you had the classical formulation, the laws, the cycles, the steam tables, the Rankine cycle, all of that practical engineering machinery that was powering the industrial world. On the other hand, you had statistical mechanics, this deeper theoretical layer that explained why the classical laws worked, grounding them in the behavior of atoms and molecules. And both layers were about to be tested and extended in ways that nobody anticipated, because a young patent clerk in Bern, Switzerland, was about to publish a series of papers that would reshape the entire field of physics. And one of those papers, maybe the one that gets the least attention compared to special relativity, was precisely about thermodynamics, about atoms, about proving once and for all that Boltzmann had been right. So let's talk about Albert Einstein in 1905. He's 26 years old. He's working at the Swiss Federal Patent Office in Bern, evaluating patent applications for electromagnetic devices. He's not a professor. He's not at a university. He'd tried to get academic positions and been turned down. His doctoral thesis had been rejected once already. By every conventional measure, he was a nobody, a technical clerk, third class, earning a modest salary, spending his days reading descriptions of inventions and deciding whether they were novel enough to deserve protection. And in his spare time, evenings, weekends, quiet moments at the office, he was thinking about the deepest problems in physics. In a single year, 1905, Einstein published 4 papers that each would have been enough to make a career. One introduced special relativity. One proposed that light comes in discrete packets, photons, which would eventually lead to quantum mechanics. One was his doctoral dissertation on determining molecular dimensions. And one, the one that matters most for our story tonight, was about Brownian motion. And that paper was, at its heart, a thermodynamics paper. A statistical mechanics paper. A paper that said, if Boltzmann's picture of the world is correct, if matter really is made of atoms bouncing around according to statistical laws, then here is something specific and measurable that you should be able to observe. Brownian motion itself had been known for almost 80 years by then. In 1827, a Scottish botanist named Robert Brown was looking through a microscope at pollen grains suspended in water, and he noticed that tiny particles ejected from the pollen were jittering around, dancing really in this random, ceaseless, zigzagging motion. They never settled down. They never stopped. And Brown couldn't figure out why. He tested all sorts of things, different types of pollen, mineral dust, soot, even ground up fragments of the Sphinx, if you can believe that. And the jittering was always there. It wasn't life. It wasn't some vital force in the pollen. It was something about being small and being suspended in liquid. For decades, nobody had a convincing explanation. But by the late 1800s, people started to suspect that the jittering was caused by the water molecules themselves, billions of them, smashing into the tiny visible particle from all sides. Most of the time, the impacts would roughly cancel out. But every now and then, just by chance, a few more molecules would hit from one direction than another, and the particle would get nudged, then nudged again, then again. The result was this random drunken walk, what mathematicians would later call a random walk, that you could actually see under a microscope. Here's what Einstein did that was so clever. He didn't just say atoms are bumping into the particle. He worked out the mathematics. He derived a precise prediction. If you watch a Brownian particle over time and measure how far it drifts from its starting point, the average squared displacement should grow linearly with time. And the rate of that growth depends on measurable things: the temperature of the liquid, its viscosity, the size of the particle, and on one crucial number, Avogadro's number, which tells you how many molecules are in a given amount of substance. In other words, Einstein gave experimentalists a recipe. Measure the jiggling carefully enough, and you can count atoms. You can calculate how many molecules of water are in that drop. You can weigh a single molecule. And this is where it gets beautiful, because remember the whole bitter fight that had consumed the last decades of Boltzmann's life? Mach insisting atoms were a fiction. Ostwald insisting that energy was the only real thing. The positivists demanding that science restrict itself to observable quantities and dismissing atoms as metaphysical speculation. Well, Einstein had just turned atoms into an observable quantity. He'd connected the invisible, the molecular bombardment, to the visible, the jittering of a particle you could watch through a microscope. He'd built a bridge between the two worlds. And then, a few years later, a French physicist named Jean-Baptiste Perrin did the experiments. Perrin was meticulous, patient, brilliant at experimental work. He prepared tiny uniform spheres of a resin called gamboge and mastic, suspended them in liquid, and painstakingly tracked their positions under the microscope, recording coordinates at regular intervals. Thousands of observations, and when he analyzed the data, the results matched Einstein's predictions beautifully. From the Brownian motion measurements, Perrin calculated Avogadro's number, and it agreed with estimates obtained by completely different methods, from the kinetic theory of gases, from the charge on the electron, from radioactivity measurements. All these independent paths converging on the same number, the same count of atoms. Perrin published his comprehensive results in 1909, and the effect on the scientific community was decisive. Even Ostwald, the great champion of energetics, the man who had spent years arguing that atoms were unnecessary fictions, even Ostwald conceded. In 1909, in a new edition of his textbook, he wrote that the experimental evidence for atoms, particularly from Brownian motion, had made the atomic hypothesis into a well-founded scientific theory. It was over. The debate was settled. Atoms were real. Boltzmann never saw it. He had died 3 years earlier, in 1906, during a family vacation in Duino, near Trieste. He never knew that vindication was just around the corner. And that's one of the saddest parts of this whole story. That the person who had fought hardest, who had built the deepest theoretical framework connecting thermodynamics to atomic reality, who had endured decades of professional hostility and personal anguish, didn't live to see the moment when the world finally agreed with him. Perrin won the Nobel Prize in 1926 for his work on Brownian motion and the discontinuous structure of matter. On Boltzmann's grave in Vienna, they carved his equation, S equals K log W, the formula that says entropy is about counting possibilities, the formula that turned out to be one of the most profound statements in all of physics. Now, here's the thing. Einstein's 1905 papers didn't just settle the atoms debate. They also cracked open a door into something entirely new. Because that other paper, the one about light coming in discrete packets, was pointing toward quantum mechanics. And quantum mechanics would, over the next few decades, completely transform thermodynamics, not by replacing it, but by revealing a whole new layer underneath. Let me explain what I mean. Classical thermodynamics, the stuff we've been talking about, Carnot's cycles, Clausius's entropy, Boltzmann's statistics, all of that assumed that energy was continuous, that a molecule could have any speed, any energy, smoothly varying from 0 to infinity. And for most practical purposes, that works fine. But there was a problem. A specific, nagging, embarrassing problem that had been bothering physicists since the 1890s. And it had to do with something called black body radiation. You know what a black body is, intuitively, even if you've never heard the term. Heat something up, a piece of iron, say, and it starts to glow. First a dull red, then orange, then yellow, then white hot if you get it hot enough. The color of the glow depends on the temperature, and a black body is just an idealized object that absorbs all radiation, that hits it, and emits radiation purely based on its temperature. No reflection, no special surface effects, just pure thermal emission. A perfect black body doesn't exist in nature, but a small hole in the wall of a hot oven comes very close. You look into the hole, and the light coming out is black body radiation. It depends only on the temperature of the oven walls. By the late 1800s, experimentalists had carefully measured the spectrum of blackbody radiation, how much energy comes out at each wavelength, and the results were beautifully smooth curves that shifted predictably with temperature. The challenge was to explain those curves using physics, and classical thermodynamics, combined with classical electromagnetism, couldn't do it. When physicists tried to calculate the blackbody spectrum using the established laws, they got a formula that worked reasonably well for long wavelengths, infrared light, but predicted that the amount of energy should increase without limit as you move to shorter and shorter wavelengths, toward ultraviolet and beyond. The theory said a hot oven should be blasting out infinite amounts of ultraviolet radiation, X-rays, gamma rays. Obviously, it doesn't. Your kitchen oven glows red. It doesn't kill you with gamma radiation. This catastrophic failure of classical theory was later called the ultraviolet catastrophe, and it was deeply disturbing because it meant something fundamental was wrong, or at least incomplete, in the theoretical framework. In December 1900, a German physicist named Max Planck found a way out. Planck had been working on the blackbody problem for years, trying different mathematical approaches, and he discovered that he could reproduce the experimental curves perfectly, every wavelength, every temperature, if he made one strange assumption. He assumed that the energy of the oscillators in the oven walls couldn't take on any arbitrary value. Instead, the energy had to come in discrete chunks, quanta, with each chunk proportional to the frequency of the oscillation. High-frequency oscillators could only emit or absorb energy in large chunks. Low-frequency oscillators dealt in smaller chunks. And the constant of proportionality, the number that set the size of these energy packets, is what we now call Planck's constant, usually written as h. It's a tiny number, incredibly small, which is why you don't notice quantization in everyday life. But at the atomic scale, it changes everything. Now, Planck himself was uncomfortable with what he'd done. He saw the quantization as a mathematical trick, a calculational device that happened to give the right answer. He didn't necessarily believe that energy was truly granular at a fundamental level. He spent years trying to find a way to derive the same result without the quantum hypothesis. He couldn't. And meanwhile, Einstein took the idea much further. In that 1905 paper on the photoelectric effect, Einstein proposed that light itself comes in quanta, that a beam of light isn't a continuous wave, but a stream of particles, each carrying energy equal to Planck's constant times the frequency. This was radical. This was saying that the quantization wasn't just a trick for calculation. It was a feature of reality. And this is where thermodynamics and quantum mechanics start to intertwine in really deep ways. Because think about what Boltzmann's statistical mechanics does. It counts microstates. It asks, how many ways can energy be distributed among the particles in a system? And the answer to that question depends entirely on what distributions are allowed. In classical physics, energy is continuous, so there are infinitely many possible states, and you have to be very careful about how you count them. In quantum physics, energy is discrete, the states are countable, and suddenly the counting becomes cleaner, more natural. Boltzmann's formula S equals K log W actually works better, more rigorously, with fewer ad hoc assumptions, when you use quantum mechanics to define what the microstates are. This wasn't obvious right away. It took decades to work out. But by the 1920s and 1930s, physicists like Satyendra Bose, Einstein again, Enrico Fermi, and Paul Dirac had developed quantum statistical mechanics. new ways of counting microstates that accounted for the quantum nature of particles. And it turned out that the rules for counting depend on what kind of particle you're dealing with. Some particles, photons for instance, and atoms with integer spin, follow what's called Bose-Einstein statistics, where multiple particles can pile into the same quantum state. Other particles, electrons, protons, neutrons, anything with half-integer spin, follow Fermi-Dirac statistics, where each quantum state can hold at most one particle. And this distinction, which sounds abstract, has enormous practical consequences. Think about metals, for instance. Why does copper conduct electricity so well? Why does iron become magnetic? Why do some materials become superconductors at very low temperatures, losing all electrical resistance entirely? All of these phenomena depend on how electrons, which are fermions following Fermi-Dirac statistics, fill up the available energy states in a solid. The thermodynamics of electrons in metals is quantum thermodynamics, and it explains properties of materials that classical theory simply couldn't account for. The specific heat of metals at low temperatures, for example, classical theory predicted it should be much larger than what experiments measured. The quantum theory of electrons in metals, worked out by Arnold Sommerfeld in the late 1920s, explained the discrepancy perfectly. And then, there's the other side, Bose-Einstein statistics, which predicted something truly extraordinary. In 1924, Bose sent Einstein a paper about the statistics of photons, and Einstein extended the idea to atoms. He realized that if you cooled a gas of bosonic atoms to extremely low temperatures, something bizarre should happen. A macroscopic fraction of the atoms should all drop into the lowest possible energy state, all doing exactly the same thing at once, behaving as a single quantum entity, a new state of matter. Einstein predicted this in 1925, and it was finally achieved experimentally 70 years later in 1995, when Eric Cornell and Carl Wieman at the University of Colorado cooled a gas of rubidium atoms to less than 1/millionth of a degree above absolute zero and observed the first Bose-Einstein condensate. They shared the Nobel Prize for it in 2001. And here's the beautiful thread. That experiment is, at its core, a thermodynamics experiment. It's about what happens when you take a system to the extreme edge of temperature, to the neighborhood of absolute zero, that temperature that William Thomson first defined back in the 1840s, using Carnot's engine as a thought experiment. Which brings us to another remarkable law, the third law of thermodynamics. We've spent a lot of time with the first and second laws, but the third one is quieter, more subtle, and in some ways the most philosophically strange of them all. The third law tells you something about the destination that absolute zero represents. Not just that it's very cold, but that it's fundamentally unreachable. And the story of how we figured that out is one of those slow burn realizations that took decades to fully crystallize. The person most associated with the third law is Walther Nernst, a German physical chemist who was, by all accounts, a character. Short, round, enormously confident, and absolutely brilliant. Nernst was the kind of scientist who moved between disciplines like he owned them all. He made contributions to electrochemistry, to chemical thermodynamics, to solid-state physics. He won the Nobel Prize in Chemistry in 1920, and he was famously practical. He patented an electric lamp, the Nernst lamp, that actually competed with Edison's incandescent bulb for a while. He drove one of the first automobiles in Göttingen and reportedly terrified his colleagues with his driving. But his deepest contribution to science was something he announced in 1906, which he initially called his heat theorem. It took years of refinement by Nernst himself and others before it became what we now call the third law of thermodynamics. Here's the problem Nernst was trying to solve. Chemists in the early 1900s needed to predict whether a chemical reaction would happen spontaneously. They knew from thermodynamics that this depended on something called the free energy of the reaction, a quantity that combines the energy change and the entropy change. You need both pieces, and the energy part was relatively straightforward to measure with calorimeters. But the entropy part was tricky, because entropy calculations always involved an unknown constant, an arbitrary baseline. It was like trying to measure altitude without agreeing on where sea level is. You could calculate entropy changes, differences, but you couldn't pin down the absolute entropy of a substance. And that missing baseline meant you couldn't fully predict whether a reaction would go forward or not without doing the actual experiment. Nernst's insight, drawn from careful experiments on chemical reactions at low temperatures, was that as you approach absolute zero, the entropy change in any process between pure crystalline substances approaches zero. In other words, the entropies of different substances converge as temperature drops towards zero. They all approach the same value. And eventually, Max Planck extended this idea to its clean, elegant conclusion. The entropy of a perfect crystal at absolute zero is exactly zero. That's the third law in its most common modern form. At absolute zero, a perfect crystal has zero entropy. Now think about what that means in Boltzmann's language. Entropy equals K times the logarithm of the number of microstates. If entropy is zero, then the logarithm of the number of microstates is zero, which means there's exactly one microstate. 1. At absolute zero, a perfect crystal is in its single lowest energy configuration. There's no randomness, no disorder, no ambiguity about where anything is or what it's doing. Everything is perfectly ordered. That's a beautiful connection. Nernst's experimental observation about chemical reactions at low temperatures maps directly onto Boltzmann's statistical framework. The universe, at absolute zero, has only one way to arrange itself, and here's the practical payoff that Nernst cared about. If you set entropy to zero at absolute zero, you've established your sea level. Now you can calculate absolute entropies for any substance at any temperature by measuring how much heat you have to add to warm it up from zero. Chemists could finally fill in that missing piece and predict the direction of reactions from tabulated data alone. It was an enormous practical advance for chemistry and chemical engineering. Every thermodynamic table you've ever seen in a chemistry textbook, those columns of standard molar entropies, they all rest on the third law. They all assume that baseline of zero entropy at 0 Kelvin. But the third law has another implication, one that's more profound and a little haunting. It implies that you can never actually reach absolute zero. Not just that it's hard, that it's impossible, even in principle. You can get asymptotically close, always having the remaining distance, shaving off another fraction of a degree, but you can never arrive. It's like a horizon that recedes as you approach it. Every cooling method becomes less and less efficient as you get closer to zero. Each successive step requires more effort for a smaller gain. This is sometimes stated as the unattainability formulation of the third law. No finite sequence of processes can bring a system to absolute zero in a finite number of steps. And experimentally, this is exactly what people have found. The history of cryogenics, the science of reaching extremely low temperatures, is a history of heroic effort to get closer and closer to that unreachable point. In the late 1800s, scientists raced to liquefy gases. Oxygen was liquefied in 1877, nitrogen around the same time, hydrogen in 1898 by James Dewar in London. But the last holdout was helium, which has the lowest boiling point of any element, about 4 Kelvin, 4 degrees above absolute zero. The race to liquefy helium became one of the great scientific competitions of the early 20th century. The winner was Heike Kamerlingh-Onnes, a Dutch physicist working at the University of Leiden. In 1908, he succeeded in liquefying helium for the first time, reaching temperatures below 5 Kelvin. It was a monumental achievement, and it opened up an entirely new frontier of physics. Because once you have liquid helium as a coolant, you can start exploring what matter does in that extreme cold. And what Kamerlingh-Onnes found, just 3 years later in 1911, was genuinely shocking. He was measuring the electrical resistance of mercury as it cooled, expecting it to decrease gradually. Instead, at about 4.2 Kelvin, the resistance didn't just decrease, it vanished, completely, to zero. Not approximately zero, not very small, zero. He had discovered superconductivity. This was something that classical physics had absolutely no framework to explain. A material with literally no electrical resistance, a current that, once started, would flow forever without any energy input. It seemed to violate everything engineers knew about how the world worked. And it took decades, until 1957, before John Bardeen, Leon Cooper, and Robert Schrieffer developed the BCS theory that explained superconductivity as a quantum phenomenon. At sufficiently low temperatures, electrons in certain materials pair up into what are called Cooper pairs, and these pairs behave as bosons. There's that word again, the same category of particles that gives us Bose-Einstein condensation. The Cooper pairs condense into a single quantum state, a coherent collective that can flow without scattering, without resistance. It's quantum thermodynamics made tangible, and it matters enormously in the real world. Superconducting magnets are what make MRI machines work, what make particle accelerators like the Large Hadron Collider possible. Every time someone gets a brain scan at a hospital, they're lying inside a magnet cooled by liquid helium to a few degrees above absolute zero, exploiting a phenomenon that only exists because of the quantum thermodynamics that grew out of Boltzmann's statistics and Nernst's third law. Kamerlingh-Onnes also discovered something else strange about helium. When you cool liquid helium below about 2.2 Kelvin, it undergoes a phase transition into a state called a superfluid. Superfluid helium flows with zero viscosity, no internal friction at all. It can climb up the walls of a container and spill over the edge. It can flow through channels so narrow that any normal liquid would be stopped cold. Again, this is a macroscopic quantum phenomenon, deeply connected to Bose-Einstein statistics, because helium-4 atoms are bosons. The superfluid state is essentially a Bose-Einstein condensate in liquid form. And the thermodynamics of this transition, the way the specific heat of helium spikes at that critical temperature in a shape that physicists call the lambda point because the graph looks like the Greek letter lambda, became one of the key testing grounds for our understanding of phase transitions and critical phenomena throughout the 20th century. So here we are, in the territory where thermodynamics meets quantum mechanics, meets the most extreme conditions humans can create in a laboratory. And this is where the story takes an interesting modern turn, because thermodynamics in the 20th and 21st centuries didn't just stay confined to engines and chemical reactions and cryogenics. It expanded into territory that would have been unimaginable to Carnot or Clausius or even Boltzmann. It reached into information itself. The person who made that leap was Claude Shannon, an American mathematician and electrical engineer working at Bell Labs. In 1948, Shannon published a paper called A Mathematical Theory of Communication, and it essentially created the field of information theory from scratch. What's remarkable, and what matters for our story, is the mathematical framework Shannon used. He needed a way to quantify information, to measure how much information is contained in a message, and the formula he arrived at looked almost identical to Boltzmann's entropy formula. Not vaguely similar, structurally the same. A sum over probabilities times logarithms of probabilities. Shannon actually called his quantity entropy, and there's a famous anecdote, maybe apocryphal but widely told, that John von Neumann advised him to use the word entropy because, quote, nobody really knows what entropy is, so in a debate you will always have the advantage. Whether or not that conversation actually happened, the connection is deep and real. Shannon's information entropy measures uncertainty. How surprised you'll be, on average, by the next symbol in a message. Boltzmann's thermodynamic entropy measures the number of microscopic arrangements consistent with what you observe. Both are fundamentally about what you don't know. Both measure missing information. And this wasn't just a cute analogy. Starting in the 1950s and 1960s, physicists like Edwin Janes argued forcefully that thermodynamic entropy literally is information entropy, that the second law of thermodynamics is, at its deepest level, a statement about inference and probability, about what you can and cannot predict given limited knowledge of a system. This perspective, sometimes called the information theoretic interpretation of thermodynamics, reframed the entire field. Entropy isn't a mysterious substance. It isn't a fluid. It isn't even really about disorder, despite what every introductory textbook says. It's about counting possibilities. It's about what you don't know. And this brings us to one of the most delightful thought experiments in all of physics, one that connects thermodynamics and information in a way that puzzled the greatest minds for over a century. It's called Maxwell's Demon, and it was dreamed up by none other than James Clerk Maxwell himself, back in 1867. The idea is simple and devious. Imagine a box divided into two halves by a wall, with a tiny door in the wall. The box is full of gas at a uniform temperature. Now imagine a tiny intelligent being, the demon, who can see individual molecules. When a fast molecule approaches the door from the left, the demon opens it and lets the molecule through to the right. When a slow molecule approaches from the right, the demon lets it through to the left. Over time, the fast molecules accumulate on one side and the slow ones on the other. One side gets hot, the other gets cold. And the demon has decreased the entropy of the gas without doing any work. The second law of thermodynamics appears to be violated. Maxwell proposed this as a thought experiment to probe the limits of the second law, and it nagged at physicists for generations. The resolution, when it finally came, was stunning in its elegance, and it came from thinking about information. In 1961, Rolf Landauer at IBM showed that erasing information, not acquiring it, but erasing it, has an unavoidable thermodynamic cost. Every bit of information you erase must dissipate at least a tiny amount of energy as heat. This is called Landauer's principle. And in 1982, Charles Bennett showed that this is what saves the second law from Maxwell's demon. The demon has to observe, record, and eventually erase information about each molecule it sorts. That erasure generates entropy, at least as much entropy as the demon's sorting reduces. The books balance. The second law survives. And the deep reason it survives is that information is physical. It's not abstract. It's not ethereal. Storing and erasing information are physical processes with real thermodynamic consequences. This idea that information is physical, that computation has thermodynamic costs, that entropy and ignorance are two faces of the same coin, has become one of the most fertile areas of modern physics. It connects thermodynamics to computer science, to quantum computing, to black hole physics. When Stephen Hawking showed in the 1970s that black holes have a temperature and an entropy proportional to the area of their event horizon, he was extending thermodynamics into general relativity and quantum gravity. The so-called black hole information paradox, which asks what happens to information that falls into a black hole, is at its heart a thermodynamics problem. It's the second law, dressed up in the most extreme conditions the universe can offer. And there's something wonderful about that trajectory, if you think about it. A subject that began with practical questions about how to get more useful work out of a steam engine, Carnot in 1824, trying to help French industry compete with British industry, has expanded to encompass the fundamental nature of information, the quantum behavior of matter near absolute zero, and the thermodynamics of black holes at the edge of spacetime. The laws haven't changed. The first law still says energy is conserved. The second law still says entropy tends to increase. The third law still says you can't reach absolute zero. But the meaning of those laws, the depth of what they're really telling us about the universe, has grown and grown and grown. Which makes you wonder, is thermodynamics finished? Is it a closed book, a completed chapter in the history of science? And the answer is emphatically no. Some of the most exciting work happening right now, in labs and on blackboards around the world, is pushing thermodynamics into new and unfamiliar territory. There's a whole field called stochastic thermodynamics that deals with what happens when systems are so small that the usual laws become probabilistic rather than absolute, when a molecular motor inside a living cell can occasionally run backward, when entropy can temporarily decrease in a tiny pocket of the universe, not because the second law is wrong, but because at that scale, it's a statement about what's overwhelmingly likely rather than what's absolutely guaranteed. And that distinction between guaranteed and overwhelmingly likely doesn't matter when you're talking about a steam engine or a power plant or even a cup of coffee cooling on your desk, because those systems involve so many trillions of molecules that the probability of entropy spontaneously decreasing is so vanishingly small, it might as well be zero. But shrink your system down. Shrink it way, way down to the scale of a single protein folding inside a cell, or a molecular motor dragging cargo along a filament, or an enzyme catalyzing a reaction one molecule at a time. Now you're in a regime where thermal fluctuations are comparable to the energy scales of the process itself, and suddenly the second law isn't a rigid commandment anymore. It's more like a strong tendency. A very, very strong tendency, but a tendency nonetheless. This is the world that stochastic thermodynamics was built to describe, and it's genuinely one of the most exciting frontiers in physics right now. The key breakthrough came in the late 1990s when a physicist named Christopher Jarzynski, working at Los Alamos National Laboratory, derived something remarkable. He showed that you could connect the free energy difference between two equilibrium states, a quantity that classical thermodynamics says you can only measure through a reversible process, to measurements made during irreversible processes, messy, out of equilibrium, real-world processes, as long as you repeated the measurement many times and averaged in a very specific way. This is called the Jarzynski equality, published in 1997, and it was surprising because classical thermodynamics had always drawn a hard line between reversible and irreversible. Reversible processes were the idealized gold standard, the ones that let you extract maximum work and calculate exact free energy changes. Irreversible processes were the messy reality, and classical thermodynamics could only give you inequalities about them. Work is at least this much. Free energy changes by at most that much. Jarzynski showed that the inequality could be replaced by an exact equality, but only if you thought statistically, averaging over many repetitions of the same irreversible process using an exponential weighting that gives extra importance to the rare runs where things go unusually well, where by chance the system happens to behave almost reversibly. Around the same time, Gavin Crookes, then a graduate student at Berkeley, derived a related result called the Crookes fluctuation theorem, which gives you the precise ratio of the probability of a forward process to the probability of its time-reversed counterpart. And what's beautiful about Crookes's result is that it contains the second law as a special case. When you take the limit of large systems, many particles, macroscopic amounts of energy, the probability of the reverse process becomes so astronomically small compared to the forward process that you recover the familiar statement, entropy increases, period, end of story. But for small systems, the reverse process has a non-negligible probability, and the fluctuation theorem tells you exactly how non-negligible. These aren't just theoretical curiosities. They've been tested experimentally, directly, in labs. In 2002, a group of researchers in Australia, led by Dennis Evans and Edith Sevick, along with their student Zhenmayo Wang, performed an experiment where they used optical tweezers, focused laser beams that can grab and manipulate microscopic objects, to drag tiny latex beads through water. They measured the entropy production along individual trajectories, and they found exactly what the fluctuation theorems predicted. Most of the time, entropy increased, as you'd expect, but a small fraction of the time, over short durations, entropy decreased. The second law was being violated, right there in the lab for brief moments, at tiny scales. And the statistics of those violations matched the theory perfectly. Think about what that means for a second. For a century and a half, the second law of thermodynamics was treated as perhaps the most ironclad principle in all of physics. Arthur Eddington's famous quote, that if your theory contradicts the second law, there's no hope for it, reflected a near-universal attitude. And now, here were experimenters watching entropy run backward, in real time, in a controlled experiment. Not because the second law was wrong, but because we finally had the tools and the theory to understand what the second law really means at the smallest scales. It's a probabilistic law. It always was. Boltzmann knew that way back in the 1870s when he first connected entropy to probability. But it took over 100 years for the mathematical framework to catch up, to give us exact, testable predictions about how and when and how often the law would appear to be violated. And here's where this connects to something deeply practical and deeply fascinating: biology. Living cells are exactly the kind of small, far from equilibrium systems where stochastic thermodynamics matters. A molecular motor like kinesin, which walks along microtubules inside your cells carrying organelles and vesicles, operates at energy scales where thermal noise is significant. Each step it takes involves converting the chemical energy of ATP hydrolysis into mechanical work, and the efficiency and reliability of that process can only be properly understood using the tools of stochastic thermodynamics. The same goes for the ribosome, that astonishing molecular machine that reads messenger RNA and assembles proteins amino acid by amino acid, or ATP synthase, the rotary motor embedded in your mitochondrial membranes that synthesizes most of the ATP your body uses. These are heat engines, in a very real sense. They're Carnot's descendants, operating not with pistons and cylinders, but with conformational changes in protein structures, powered by chemical gradients, working at the nanoscale where fluctuations are part of the operating environment rather than a nuisance to be minimized. There's a whole emerging field sometimes called biological thermodynamics, or the thermodynamics of life, that's trying to understand how living systems manage to maintain their extraordinary order and complexity in a universe that's constantly pushing toward equilibrium. And the answer isn't that life violates the second law. It emphatically doesn't. The answer is that life is spectacularly good at coupling processes together, at using the entropy increase from one process to drive the entropy decrease in another, at maintaining itself far from equilibrium by constantly dissipating energy and exporting entropy to its surroundings. You eat food, you breathe oxygen, you radiate heat, and all of that entropy production is what pays for the astonishing molecular order inside every one of your cells. The second law isn't life's enemy. It's the backdrop against which life performs its most impressive tricks. And speaking of modern frontiers, there's another direction where thermodynamics is pushing into genuinely new territory, and it connects back to something we talked about earlier: the relationship between thermodynamics and information. Remember Landauer's principle, the idea that erasing a bit of information has a minimum thermodynamic cost? Well, in the last couple of decades, researchers have been exploring the flip side of that coin. If erasing information costs energy, then having information about a system, knowing something about its microscopic state, can be used as a kind of resource. You can extract work from a system that you know something about, work that you couldn't extract if you were ignorant. This has been demonstrated experimentally. In 2010, a group led by Shoichi Toyabe in Japan built a microscopic version of a Szilard engine, a thought experiment that Leo Szilard proposed in 1929 as a simplified version of Maxwell's demon, and showed that they could convert information into actual mechanical work. They watched a tiny bead on a staircase-like energy landscape, and by measuring which direction the bead had fluctuated, and then raising the stair behind it at just the right moment, they could make the bead climb upward, effectively extracting energy from thermal fluctuations using information as fuel. The amount of energy they extracted per bit of information used was exactly consistent with Landauer's limit. This is wild if you think about it. Information, something we usually think of as abstract, intangible, the stuff of hard drives and text messages, has a concrete, measurable thermodynamic value. A bit of information, used cleverly, is worth kT times the natural log of 2 in extractable work, where K is Boltzmann's constant and T is the temperature. That's a tiny amount of energy per bit at room temperature, about 3 times 10 to the minus 21 joules. But it's real, it's measurable, and it's fundamental. It means that the boundary between physics and information theory isn't just a useful analogy. It's a physical law. And this has implications that ripple outward into computing, into biology, into our understanding of what it means to process information in a physical universe. Every computation your laptop performs, every neural firing in your brain, every time a ribosome reads a codon and selects the right amino acid. All of these are physical processes that involve acquiring, storing, transforming, and sometimes erasing information, and all of them are subject to thermodynamic constraints. The theoretical minimum energy cost of computation, set by Landauer's principle, is far, far below what any current computer actually uses. Modern transistors dissipate something like 1,000,000 times more energy per operation than the Landauer limit. But as computers continue to shrink and become more energy efficient, that fundamental floor becomes more and more relevant. Some researchers think that the thermodynamics of information will be one of the key constraints shaping the future of computing technology, especially as we push toward molecular scale and quantum computing. Quantum thermodynamics, in fact, is another frontier worth mentioning, even briefly. When you get down to the quantum scale, the very concepts of work, heat, and temperature become slippery. A quantum system can be in a superposition of energy states. It can be entangled with other systems, and measurement itself disturbs the system in fundamental ways. Defining what it means for a quantum system to do work or exchange heat requires careful thought, and there's an active and lively debate about how to extend thermodynamic concepts into the fully quantum regime. Some researchers are exploring quantum heat engines, theoretical devices that use quantum coherence or entanglement as a resource, potentially operating in ways that have no classical analog. Whether these quantum effects can actually enhance performance beyond classical limits, or whether the second law always finds a way to reassert itself, is an open question. But the fact that we're asking it, that thermodynamics is being stress-tested against quantum mechanics in this way, tells you something about how alive and dynamic the field still is. So let's step back for a moment. Let's take a breath and think about the arc of this whole story, because it really is remarkable. We started with fire, with the simple, ancient observation that heat can make things move. And from that practical, almost primitive starting point, a chain of thinkers, Carnot, Joule, Thomson, Clausius, Rankine, Boltzmann, Planck, Einstein, Nernst, Shannon, Landauer, Hawking, Jarzynski, and so many others, built a framework that reaches from the Industrial Revolution to the event horizons of black holes, from the steam engines of 19th century Britain to the molecular motors inside your own cells, from the abstract mathematics of probability theory to the physical reality of information and computation. And the beautiful thing, the thing I keep coming back to, is that the core ideas are so simple. Energy is conserved. Entropy tends to increase. You can't reach absolute zero. 3 statements. You could fit them on an index card. But the depth contained in those 3 statements is essentially bottomless. Every generation of physicists and engineers has found new meaning in them, new applications, new surprises. Carnot thought he was studying steam engines. He was really uncovering a universal law about the limits of efficiency. Boltzmann thought he was explaining why gases behave the way they do. He was really discovering the statistical foundation of irreversibility and the arrow of time. Shannon thought he was solving a problem in telecommunications. He was really revealing that entropy and information are 2 faces of the same coin. That's the thing about thermodynamics. It keeps showing up. It keeps being relevant in contexts that its founders couldn't possibly have imagined. And if history is any guide, it will keep showing up in the physics and engineering and biology of the future, in ways that we can't yet imagine either. But for now, for tonight, you don't need to imagine any of that. You've followed this story a long way, from Carnot's water wheels to Boltzmann's tombstone, from Joule's brewery to Hawking's black holes, from the clatter of early steam engines to the quantum hum of atoms chilled to billionths of a degree above absolute zero. That's a lot of ground to cover, and if you drifted in and out, if you caught some parts and missed others, that's perfectly fine. The ideas will be there whenever you want to come back to them. They've been waiting since the universe began, really. The laws of thermodynamics aren't going anywhere. So let your mind settle now. Let the concepts blur a little, the way they naturally do when you're this relaxed. If there's one image to hold on to as you drift off, let it be this. Every process in the universe, from the grandest supernova to the gentlest breath you're taking right now, is part of the same great story of energy transforming, entropy flowing, and the universe slowly, patiently finding its way toward equilibrium. You're part of that story. Every warm breath you exhale into the cool night air is thermodynamics in action. Your body exporting entropy, maintaining the beautiful, improbable order that makes you, you. And there's something deeply comforting about that, I think, knowing that the same laws that govern stars and engines and black holes are quietly, gently at work in you, right now, as you rest. So rest. The universe will keep running. The entropy will take care of itself. And you can just sleep.